In pursuit of transferring technical knowledge and just to gear up the new engineering entrant, myself Pranav is here to deliver today's presentation, Power Transformer Part 79. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with winding configuration affects polarization forces, right? The winding configuration of a transformer would responsible to have a direct effect on the electric field distribution within the insulation, which in turn influences dielectric polarization forces. Transformer windings can be classified in two common winding configurations. One, concentric windings. Two, helical or spiral windings. Three, interleaved windings, sometimes referred to as sandwich or pancake windings. The specific configurations, such as concentric versus interleaved windings, that are being designed to accommodate all electric field stresses in a different perspective of their constructional features. Transformer winding types and suitability would have to depend on system voltage, load type, and performance requirements. However, the selection of transformer winding type and thereof corresponding connections, that is star or delta, both are crucial for determining a transformer's suitability for specific applications and its operational characteristics. The windings that are to conduct current and the number of turns directly dictates the induced voltage. A transformer, as it works as the principle of mutual induction, which is based on Faraday's law of electromagnetic induction. So, the induced voltage is thereby directly proportional to the number of turns, that is, V is directly proportional to N. Winding types and suitability can be categorized with the following design understanding. One, need of balance voltage, need to balance voltage and current, mechanical strength, cooling arrangement, system application. The transformer engineering selection of transformer winding layout is being much crucial, as because this will directly affect the underneath factors: voltage levels, current levels, phase shifts, harmonic behavior, natural availability or neutral availability, application suitability, impacting performance, and parallel operation. Again, I repeat: voltage levels, current levels, phase shifts, harmonic behavior, neutral availability, application suitability, impacting performance, and parallel operation. So, the precise arrangement of winding distribution is the fundamental design choice for improving efficiency, reducing harmonics, and enhancing reliability by shaping the magnetic field, optimizing current flow, and ensuring uniform cooling and mechanical strength. Optimizing winding layout for best possible core utilization that involves a multi-objective design process to configure the optimum enhancement of core's function for transferring or storing magnetic energy. This has been achieved by operating the core near its saturation limit while managing core losses, that is hysteresis and eddy current losses, and similar losses, that is copper losses, within the acceptable thermal limits. That has made to ensure efficient energy transfer by managing parameters like leakage inductance and resistance. Polarization losses are primarily related to the dielectric properties of insulation materials, whereas the winding layout influences the magnetic field distribution that causes to affect the magnitude of eddy currents induced in the conductors. The main component of AC loss in windings is the slot leakage flux, which are caused by the alternating magnetic field within the slot, inducing eddy currents in the conductors due to skin and proximity effects, causing to increase AC resistance and lead to energy dissipation as heat, that is eddy current loss. Therefore, optimization of winding layout primarily relates to the control the magnetic fields by arranging the winding positions in such a way that they are not to be placed in close proximity to the ends of the core. Again, I repeat, optimization of winding layout primarily relates to control the magnetic fields by arranging the winding positions in such a way that they are not to be placed in close proximity to the ends of the core. Such winding arrangements that are made to reduce the influence of stray magnetic fields on the winding conductors. It is quite evident that the physical arrangement and design of the windings directly influence the electric field distribution throughout the insulation system. Most important. Any concurrence of non-uniform electric field distribution can give rise to localized regions of elevated electric field stress, particularly at winding edges and corners, interturn gaps, conductor crossover points. Elevated electric field strength in specific regions would thus to intensify the process of localized polarization losses, thereby converting electrical energy into heat and contributing to overall energy loss within a dielectric material. The issue of polarization losses in a transformer's insulation, oil and paper is therefore directly dependent on the electric field stress as being developed on the overall insulation structure. So, polarization losses are indirectly influenced by the winding layout as it determines the magnitude and distribution of electric field stress in the transformer's insulation structure. Major factors relate to enhance dielectric polarization losses. Dielectric loss in a transformer is the summation of underneath losses within its insulating material, that is oil and paper, when it is subjected to an alternating electric field. 1. Polarization loss. 2. Conductivity loss, also known as leakage current loss, and ionization loss. As of the analysis of operational transformer, polarization losses that are to be accounted for a very small fraction of the total transformer losses, typically less than 0.3%. Polarization phenomenon in transformer insulation refers to the molecular response of the insulating material to an applied electric field. Under the direct influence of the applied alternating electric field, polarization losses in a transformer are normally caused by the continuous alignment and realignment, that is, polarization of molecules within the transformer's insulating material like oil and paper. These dipoles alignment and realignment process would have to create a flow of current, that is polarization current, that includes capacitive, absorption, and conduction components. Three components: conductive, that is capacitive, absorption, and conduction components. The capacitive charging current, which is the initial surge of transient current, that is the transient current that flows when a voltage is first applied to an insulated system and then decays exponentially over time. Capacitive current is a large and very high initial surge that charges the physical capacitance of an insulator, decaying almost instantly. After decaying the capacitive current, there may have still to persist some tiny amount of current in transformer insulation, which is comparatively lower than the capacitive current, actual capacitive current rather. This small current is actually associated with the low rate of polarization process, that is dipole polarization and interfacial polarization within the dielectric material. This current component is thus to refer as the absorption current, and unlike capacitive charging current, it can take much longer time to decay. The absorption current is associated with the gradual polarization of molecules within the insulating material. Consequently, it is more pronounced in multi-layer oil paper insulation systems, particularly in transformer applications. The magnitude and rate of decay of the absorption current would have become highly sensitive to the presence of moisture and contaminants in the oil paper insulation. Increased moisture and contaminants in oil paper insulation system would cause to have a higher conductivity along with an increased absorption current magnitude. However, presence of high moisture concentration in oil paper insulation system that has to involve in increasing the amount of trapped charge during voltage application. In turn, Such happenings would significantly lead to effect on the trap charge in oil paper insulation by increasing conductivity and decreasing trap depth. That will cause to accelerate charge accumulation and dissipation, leading to faster space charge establishment and also to disappear in quick succession once the voltage is removed. There be the reason where the presence of moisture within the insulation, oil and paper, that would accelerate the polarization and depolarization processes, which causes the absorption current to decay faster. Similar to moisture, solid and liquid contaminants in transformer insulation such as fibers, metal particles, and sludge reduce the surface resistivity of cellulose components and increase the overall conductivity, leading to have higher and more sustained absorption currents. In the context of the total polarization current, it is quite evident that the conduction current is a critical steady state component of the total current in dielectric materials. Unlike the capacitive and absorption currents, which decay either instantly or over time, the conduction current would have to remain constant as long as the voltage is applied. It specifically represents the leakage component of the total current flowing through solid, that is solid insulation, that is pasteboard or paper, or liquid dielectric insulation, oil, which would have to increase with the deterioration of the material's dielectric properties or with the presence of moisture. Conduction current in the context of polarization current flowing through the transformer insulation represents the steady flow of charge carriers, that is ions or electrons, through the insulating medium when subjected to an electric field. As of the solid insulators, that is pasteboard and paper, conduction current is mainly caused by the movement of a small number of free electrons or ions that are not firmly bound to atoms. Whereas in insulating liquid oil, this current is primarily caused by the migration of ions. The magnitude of the conduction current is directly proportional to the applied voltage and depends on the ionic conductivity of the insulation. The conduction current in insulation is heavily influenced by the presence of moisture, acidity, and contamination. The presence of these three factors would have a direct impact by increasing conductivity and conduction current. Substantial distortion of the electric field, localized concentration of electric stress within the insulation material. The conduction current in insulation that has to further expedite under the corresponding rise of temperature, electric field strength, and subsequent physical condition of the insulation system. Presence of moisture has been considered as one of the main influencing factors that determine the conduction processes and electric strength of an insulating material. Impact of moisture on polarization losses. Based on electric theory, sorry, based on dielectric theory and experimental studies of electrical insulation, it is observed that an increase in moisture content in insulating materials leads to a higher dielectric constant and higher electrical conductivity. The presence of water droplets or thin moisture films within the insulation has therefore made to create regions with a much higher dielectric constant than the surrounding materials like epoxy or polymer insulation. This pronounced dielectric mismatch causes a substantial distortion of the electric field, leading to produce localized concentration of electric stress. The high field strength near the droplets can exceed the dielectric strength of the surrounding air or insulation, initiating partial discharge. Most important. Particularly in high voltage transformers, water droplets that form on the surface of the insulating material can have the ability to experience significant deformation when subjected to an external alternating electric field. Water droplets on insulating surfaces may have to elongate and stretch along the field lines or move to oscillate at twice the power frequency. Elongation of water droplets on insulating surfaces is one of the fundamental physical phenomenon that occurs while exposed to external electric field. The conductive water droplet, as they are to be elongated along the field lines, whose curvature rather would have become non-uniform and typically characterized by by its leading and trailing edges. However, the specific shape and curvature of water droplet depend on different types of forces acting upon it, such as electric field strength, surface tension, viscous forces, flow conditions, and interactions with contact surfaces. The electric field around a conductive object, such as water droplet, tends to intensify or become stronger at the sharp tips of the subject droplet. The electric field would have become intensified at the sharp tip primarily due to the geometric effect of charge concentration at areas with a small radius of curvature. Such phenomenon is followed by an application of fundamental principles in electrostatics, where the surface charge density and the electric field strength are inversely related to the local curvature of a conductor's surface. Again, I repeat, such phenomenon is followed by an application of fundamental principles in electrostatics, where the surface charge density and the electric field strength are inversely related to the local curvature of the conductor's surface. At a sharp tip, it is obvious that the surface area available for charges is minimal, forcing the surface charge intensity or surface charge density to become extremely high. The presence of water and its droplets would thus to disrupt the uniform field distribution, creating localized high stress points which can trigger electrical discharges at the specific contact points of water droplets and the surface of a solid insulating material. Repeated electric discharges can cause insulation degradation through physical and chemical erosion, leading to increased conductivity and eventual failure of the insulating material. Process of water droplet deformation mechanism is being continued mainly through the general understanding of fundamental principle of electrohydrodynamics. Selective analysis as relate to impact of moisture. One, behavioral aspects of water droplets are primarily influenced by the polar nature of water molecules and the electrical forces as imposed on them. Water has a very high relative permittivity, significantly higher than that of typical solid insulation materials. In a heterogeneous dielectric system where water droplets adhere to insulation material, the electric field lines tend to intensify the paths of highest permittivity to minimize potential energy. At the electric field lines would have been effectively attracted and focused by the highly polarized water droplets so that so that would create a localized intensification of the electric stress within and immediately surrounding the droplets. Concentration of localized dielectric field stress while exceeds the average field strength across the solid insulation, then those specific highly stressed regions are prone to localized dielectric breakdown, partial discharges, or tracking, which progressively degrades the material's physical and chemical composition and ultimately leads to the failure of the entire insulation system. The increased mobility of polar water molecules and water facilitated mobile ions within the complex oil paper insulation system leads to their accumulation at the interfaces between the oil and the solid cellulose insulation. Elevated water content promotes more charge accumulation and migration under an applied electric field, thereby intensifying interfacial polarization losses and associated thermal effects. Under alternating current fields, these additional polarizations result in higher dielectric losses, causing to accelerate insulation degradation and increase the risk of eventual transformer failure. Presence of water molecules can also have the tendency to migrate the mobile ions through an insulating material and accumulate to form continuous conductive pathways. As these ions migrate under an applied dielectric field, they can aggregate or align to form chains or channels of charged species, allowing current to flow more easily. Oil impregnated paper and pressboard are the most common types of solid insulations in power transformers, and the formation of these pathways has thus to bypass the high intrinsic resistance of the bulk insulating material, leading to a sharp increase in electrical conductivity. Under an applied electric field, there would have a small there would have a sorry there would have a small resistive current to flow through these conductive pathways as formed within the solid insulating materials, which is rather identified as the leakage or conduction current. Trapped charges build up within the solid insulating materials, altering the local electric field and increasing conduction current. The energy dissipated as heat because of this flow of current through the dielectric materials is referred to as conduction loss or leakage loss, which contributes significantly to the overall total dielectric loss in addition to the energy dissipated through molecular polarization processes, that is polarization losses. Let's stop here, further to be continued at later stage. Thank you for listening the video. Kindly do like, share and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you. Thank you for patient hearing.